Ben Deniz hocamızı kısaca size tanıtayım. Deniz hocam şu anda Imperial College Londra'da öğretim üyesi. 2007 yılında New York Üniversitesi Teknik'ten doktorasını aldı. Sonra çok çeşitli kuruluşlarda, çok çeşitli araştırma merkezlerinde özellikle haberleşme, kablosuz haberleşme alanında çalışmalar yürüttü. 2010'lu yılların ortasından itibaren sanırım makine öğrenmesiyle ilgili de çok yoğun araştırmalar yürütmekte. Konuşma başlığı zaten kendisini anlatıyor. Learn to communicate, communicate to learn. Ben davetimizi kabul ettiği için hocama çok teşekkür ediyorum. Hocam söz sizde.
Teşekkürler.
Sağ olun hocam.
Çok teşekkürler. Tabii öncelikle davet için çok teşekkür ediyorum. Tabii ki orada olmayı çok isterdim. Öyle de planlıyordum ama maalesef yarın bizim ana konferansımız Information Theory konferansı için bir seyahat etmem gerekti. Daha öncesinde maalesef gelemedim. Behçet hocama da çok teşekkür ediyorum. Hem sunum, introduction hem de daveti için. Söylediği gibi benim konuşmamda daha çok makine öğrenmesi uygulaması olarak yani biz daha çok uygulamasını yapıyoruz ve haberleşme alanına ve hani konuşmada benim yani vermek istediğim ana mesaj haberleşme ve öğrenme arasındaki çok yakın ilişki olacak. Şimdiden de özür dileyerek konuşmayı da İngilizce yapacağımı söyleyeyim. Tabii Türkçe yapmayı isterdim bu İstanbul'daki bir toplantı için ama pek güvenemedim açıkçası terimlerin birçoğunun Türkçesine hakim olamadığım için. Umarım sizin için de sorun değildir. Okay, so let me start with this a little bit philosophical introduction to this, how communication and intelligence are so closely intertwined. And basically to argue for this, I use the following analogy. So as you know, the scientists believe that sometime in the past in our evolution, some favorable mutation allowed humans to develop our brains, which somehow distinguished us from the other animals, gave us the intelligence we have. So basically, I find this very similar to what we have today in machine learning. That's kind of the processing power we have, which allowed us to develop the most recent artificial intelligence revolution, where we can basically process very large models and very large data sets. Whereas if you look back at the human history, the following biggest jumps in our civilization always followed some development in communication technology. So either following the invention of writing, the language, the writing, then the printing press, then the internet, and most recently the mobile revolution. So each of these allowed us, basically enabled somehow scaling our intelligence. So it first, of course, communication allowed us to pass on, our knowledge and intelligence to other, fellow humans. Then writing allowed us to communicate through time and space and so on and so forth. So basically, communication has always been very essential to scale the human intelligence. And I argue that the same must happen in the, more on the AI front if you want to really enable artificial general intelligence and also, most importantly, scale it to devices that may not be able to, have such huge processing power or data sources. Okay, so this is already, obviously acknowledged in the machine learning domain, and so we are moving to large-scale systems as you know, our models are getting bigger and bigger. Data sets are growing. All these plots are already outdated quickly in few years. And now, just as an example, for example, the distributed AlphaGo was trained on more than 1,000 CPUs and hundreds of GPUs. And as I said, these are now even to the levels of hundreds or thousands. and it's very clear that basically we have to somehow enable these devices communicate very efficiently. But so there's maybe like a one issue here is that if we look at the machine learning literature, the way these communication systems are typically modeled are as bit pipes. So the assumption is somehow that you can connect any two devices with some reliable, error-free communication link. Whereas if you talk to communication engineers, they will tell you that this is far from the reality. So every communication system, every communication channel actually suffers from various imperfections. Noise is the most common of them. So when you send any signal, typically some form of noise is added to the signal, and the receiver has to somehow recover the original message from this noisy received signal. But on the other hand, as communication engineers, so we have been working on this for decades now, and we have actually very reliable, very robust communication systems after decades of research. So typically, these go, the theory of this, the research goes back to maybe more than 100 years ago, but the theory goes back to Shannon in 1948 paper where he introduced the information theory, identified the fundamental limits of communication, and led the way to more kind of structured design of error correction codes or compression schemes. So in a sense, these technologies help us turn the noisy channel into a reliable bit pipe. But what is typically ignored is, let's say, from a machine learning perspective, is all the complexity, all that coding, the computational complexity, also, of course, the delays that these type of communication protocols introduce. And these, of course, are essential, are very critical when we look at this learning from an end-to-end perspective. So what I argue, so this is basically the research in my lab has been mainly focusing on how we can combine, how we can look at the machine learning problem and the communication problem as one, and so somehow like formulate this as one big problem, and in a sense also both learn how to communicate in the meantime, and also we have to figure out how we can enable communication specifically for the task of learning. Because even though I said that we have all these developed communication systems, codes, modulation schemes, etc., these have been mainly designed for the purposes of content delivery. So today, if you look at our mobile phones, so we can transmit like lots of videos, images, data, but so these typically, of course, have very different characteristics and requirements compared to machine learning applications. So the main challenges here are, first, of course, the usual challenges of any communication system would have as limited bandwidth, limited energy, the noise and the interference in the system. And as I mentioned, latency is an issue, so which might not be such a critical issue if, let's say, you are sending some pre-recorded video, downloading a video from YouTube to your phone, that might be less of an issue. But if you are trying to train hundreds of devices, let's say using federated learning, many iterations, then this latency become much more of a critical issue. Privacy is already an issue both in communications and machine learning, but of course, them coming together introduces additional vulnerabilities. And of course, the size and limited information content of data sets, the fact that this data is distributed and so on and so forth. So these are, as I said, new types of challenges that we have not been used to dealing with in normal communication system design. So in this talk, of course, I'm not going to be able to go through all different ways of attacking this type of problem. So what I'll do, I'll give some examples of some of the research we've been doing in my lab, mainly to convince you that looking at these two problems jointly leads to interesting research problems, but also very practically very important problems. And here, by the way, I will assume most of you not to have too much communication background, so I'll try to explain those. Of course, I might skip some of those issues. So, I mean, it would be great if you can interrupt me and ask any question. I don't know how the logistics of that would be in an auditorium setting, but and maybe, you know, I'm assuming that most of you are already working on machine learning applications, and some of you might actually know it even better than me. But maybe one of the messages that actually applying, you know, like these tools to communication system design is a very promising direction. So for some of you looking for either research opportunities or even for future kind of employment, so I think there will be a lot of demand for someone with some domain knowledge of, you know, communication system, but also very proficient in machine learning techniques. I think that we will basically in the very near future will have a complete transformation of how our communication systems are designed and implemented. So we'll move from, you know, completely model-driven design we have today to a much more data-driven, you know, somehow both machine learning and these models coming together. Okay, so I'll try to give, you know, examples from these two types of applications. So one of them will be more focusing on distributed inference. So more, let's assuming that we can train models and how we could, you know, like then use these models to make inferences over noisy communication channels. And then I will also briefly mention about, you know, how we can actually do some training over communication channels, noisy communication channels. So let's assume now, you know, we want to do some inference over the edge. So what I mean is that, let's say you're on a car, you're on a bike, so you have some device that device might sense, you know, has some sensors, and typically, of course, right now, actually, most of the data, this IoT networks collected at the edge of the network, but the current approach is to generally offload all the data to some cloud, do the learning, training, all the, you know, that's tasked over there. And maybe, you know, we would offload sometimes, you know, like put some of the models at the edge device to the capacity of the edge device to do the inference locally there. But in many cases, local inference may not be possible. So, for example, the decision that your car would make may depend on, for example, some terrain information, some background information. So there are many examples of this actually from a more communication perspective. For example, you might be using some machine learning algorithm to do channel estimation for your communication system, which typically depends on the physical, you know, environment. So you need a model that is, you know, very specific to that environment, and that might be only available at a base station. So you might need to communicate basically to make this inference. And of course, in this case, latency is a major challenge. So how do we make decisions, you know, very quickly when the data and the model may not be collocated at the same device? So this is a one-slide summary of, you know, how we actually implement, you know, design communication systems today. So typically communication problem is, the problem is this. So you have some signal, so let's say some video signal, which you want to transmit from one point to another, and typically there is some noisy channel in between. Now, so this is, in principle, this is a functional, transformations, functional optimization problem, meaning that, so you have this input signal, it can be a continuous time signal, but typically we sample it, you know, reduce it into some finite number of samples. And in principle, we need to map this signal into some channel input that goes through the channel. I mean, this channel input, let's say if you have a wireless channel, that's what I'm going to be mainly focusing on. So this is going to be some waveform, and we typically modulate some parameters of the waveform, the frequency, amplitude, etc. So that is what the communication is embedded into. That goes through the noisy channel. The channel somehow transforms this signal, and the receiver tries to recover from that noisy signal the original message. Now, so this problem, the way we do it today, is based on, at least theoretically, goes back to Shannon's source and channel separation theorem. So as I said, Shannon looked into this fundamental limits of how much information we can communicate over channels, and how much also we can, compress data. But what he showed first, actually, before even he proved his channel coding and source coding theorems, he showed that there is no loss of optimality under some theoretical assumptions by actually dividing this problem into two sub-problems, where the first problem is a compression problem. So basically, we take the source, we completely ignore the channel, and then we say, okay, what is the minimum number of bits I can represent this signal to recover it within a certain, quality of, let's say, some fidelity measure. So this is called the source coding, the compression problem, and we can completely divide it from, separate it from the channel coding problem. Then the channel coding and the modulation problem. So this deals with how reliably can we transmit these compressed bits over the channel. Now, based on this, so this is first of all very beneficial because this gives us modularity, which is very critical in engineering design. So now we can completely separately design these two components, ignoring the other. And if somehow, for example, the channel changes, we don't need to change the source coder. So we don't need to design a different video compression scheme if we are communicating over an optical channel or a telegraph channel. It's going to be the same. We just need to design the coding scheme for that particular channel, and vice versa. Of course, if the source changes, then you don't need to change the channel coding scheme. Okay, so I said that this is without loss of optimality, but it's only in some theoretical assumptions, which one of them is that infinite block length. So this is a common assumption in, when Shannon obtained his fundamental results, which of course doesn't apply to practice. So infinite block length means that I get infinitely many samples over the channel, and I can, from the source, and I can use the channel infinitely many times. And what matters is the ratio of the two. Now, so you have limited channel uses on average per source sample, but overall you have to use many times. But in practice, this is not the case. And in practice, we know that actually this type of separation is suboptimal. And people have been looking for ways to improve that. But until recently, there was no way of doing better than this separation approach, because this is a very difficult problem. How do I map some signal into completely another signal space in an also low complexity manner and then recover the signal? Whereas this changed, let's say recently, then I'll talk about that. But let me first give the example, the application example. So the example I'll talk about is the image retrieval problem at the edge. You might be more familiar with this. So the goal is to somehow, let's say you have an image, and the retrieval goal is to find the other images in a certain database of images. And these images in the database might be taken by different cameras from different angles. People might be even wearing different things. And the goal is to identify the pictures of the same person in that database, or same object, whatever. Now we want to do this over the wireless channel. Now, why am I looking at the retrieval problem, but not, let's say, the classification problem? Why not just, take pictures and then say that, okay, I want to classify these pictures, but, somehow I want to classify it the cloud? Because in that case, actually, if you don't impose any complexity constraint, the classification can be done locally at the device, right? So I can train whatever network to the capacity of this device and then put it on the device, and the device will be, because device has access to all the information necessary. It has the picture itself. Whereas if I try to send it to the cloud, that will become a noisy picture. The cloud can only do less reliable classification. Whereas in the case of retrieval, now the camera doesn't have access to the database. So it has to, the retrieval task has to be done at the cloud. But now this, we somehow have to communicate. And you can easily see that obviously this capacity of the communication channel, how much information I can transmit and how I can transmit becomes now very critical on the, how well I can perform this task. So now we can have two different approaches to this. So the first approach would be to use the current, the way of communicating that we have today. So what is it? So I can say that, okay, so I'm going to use some channel code, some existing communication scheme over the channel. So I will try to transmit, as many bits over the channel. And then I want to turn this image that I have into bits, which I will try to transmit. So now to try, what are the bits that I need to transmit? Obviously, I don't need to transmit any more the whole image. All I need to transmit is to send the features that are most relevant for the retrieval task. And then we need to somehow compress them. But here we use some, learning aided compression, because of course the standard compression schemes would not be, designed for this. So we designed this, both the feature extraction and the compression scheme end to end. And here we are using some arithmetic coding after quantization for lossless compression. These might be a little bit details, but so basically here, the way we use learning, which is kind of standard these days for neural network aided also image compression schemes, is that we use some neural network to learn the distribution of these quantized bits so that we can exploit this arithmetic coding scheme at its optimal performance. So this is one approach. So we basically try to reduce the features relevant for the retrieval task to as few bits as possible. Then we send those bits as reliably as possible over the channel. The second approach is to now forget about all this, what we have been doing, so far. And then let's say, why don't we just learn the whole thing end to end? So I get these images, we do some feature encoding and map them directly over the symbols over the channel. So basically, in a sense, I am directly modulating the waveform, and I will try to learn that. So meaning I am not using any of these, standard modulation scheme, OFDM, TDMA, whatever is that's being used. I'm not using any of those channel codes that took us decades to design. I'm not using any, like compression scheme, etc. So I'm doing everything end to end. So this is called joint source channel coding for the purposes of this retrieval task. Now, it turns out that this latter approach is performing much better. So as I said initially, so we would expect this to be better anyway, because this is more general than doing separately, right? So separating this into two problems and designing each of them is definitely a special case of the general case. But as I told you that, so even though we knew this, so far we were not able to design any such codes that would actually achieve performance even comparable with what we could do with our code designs. So and also more. So what I'm showing here, let me first highlight this. So here, so I'm plotting the top one accuracy of this retrieval task as a function of the signal to noise ratio, meaning the quality of that communication channel. So the ideal channel would be basically, if I were to do retrieval directly on this, what would be the reliability? Again, this may not be the best retrieval model, but that's not important. So it's more, relative. So now our joint scheme, which we call this deep joint source channel coding, the blue one, and I'm here, the B is how many times I use that channel. So channel bandwidth, how much channel resources I could exploit. Of course, the more, the better. So the blue one is the deep JSCC with 256 bandwidth. So you can see that, around, even 0 dB almost, you can get pretty much noiseless performance. So you completely, mitigate the channel limitations. Whereas the separation scheme has a significant gap. And if the bandwidth reduces, the channel resources reduces, the gap even increases. Then you have even more significant gap, because because we are now going farther from that optimality of the separation, because we are, that holds only when the bandwidth is infinite, whereas now if you get smaller and smaller, this joint approach is gaining more. Now, one thing is that, of course, this how many times you use the channel also determines how much latency, because it takes you so much to communicate, or how much you exploit the channel. And so this already shows that basically this joint approach is much better. And also I would like to emphasize that in the separation approach here, I'm not even using the channel codes that we would have state-of-the-art channel codes that took us 70 years. And you may not be, familiar with the channel codes like this low density parity check codes or polar codes and so forth. So these are amazing designs, took years of research, like lots of smart people have been working on them. Whereas what we are doing here is just take some neural network, mainly just actually very simple convolutional neural networks, and train them end to end. So this shows that instead of all those, compression schemes, channel coding schemes, with a machine learning approach, you can get a much better performance with a much lower kind of development rate. And this has many, many advantages, other advantages, not just performance. One of them being actually, even if I train this for a certain channel quality, and if I change the channel quality, whereas this separation-based approach completely fails because you design a certain channel code for a certain channel quality. If the quality goes bad, you lose everything. You cannot decode anything. Whereas this approach, turns out, it gives us graceful degradation. So it has this kind of natural robustness to channel variations. Then, of course, we can always retrain this for a certain type of data sets, or for a certain type of channel, and so on and so forth. And it has made much more flexibility compared to our current much more rigid designs. Okay, so and also just to mention, so we have also been looking at this, how not just identification, but what if I wanted to send an image and reconstruct it, or a video, and we also have like very promising results that actually we can do it much more efficiently compared to what, for example, our mobile phones can do today. So again, so this is just to highlight. So two aspects actually here. So one thing is that with thanks to this machine learning advances, now we can have a complete new look at the way we designed our communication systems, and even at the level of coding systems. And also another approach and another aspect is that we also have this very different kind of constraints. For example, here very low bandwidth, because this inference has to happen very quickly, very efficiently, and that also pushes us to a regime where our current systems are even much poorer in terms of performance. Okay, so now I will talk about a very different type of application, which is again something not considered at all in today's networks. So how do we actually communicate neural networks over channels? So as I said, so many times we will have lots of examples, right? So X task, so I trained the neural network and it performs great. So this neural network has, I don't know, 100 million parameters, great. Another task again. So, but you would expect that, some device or a car, let's say using artificial intelligence, is not going to go around loaded with, hundreds, thousands of different neural networks. And many of these neural networks are also going to be location dependent or time dependent. They will be constantly changing. So what's going to happen is something I call intelligence on demand. So what our communication network should enable us is that if I go somewhere and if I need to do some task, just happens that I just want to do it there, I should be able to download the required network at that moment and use it and get the results. So this is, now, of course, this will mean that somehow we need to be able to deliver these huge networks over very limited bandwidth and very limited time over noisy communication channels. Now, this is another joint source channel coding problem because, as I said, so I mentioned that this joint source channel coding, you would have a video signal, you want to transmit, you want to decode on the other hand. Now the situation is similar, but it is slightly different. Now, for example, I might have actually some neural network at the encoder side, which I want to transmit. I want to reconstruct it somehow at the decoder. But it's a very different type of communication problem because I don't care actually to reconstruct this neural network parameters with minimum error or PSNR or whatever. All I care is that what I reconstruct, this new model at the receiver, is good for the task. It has good accuracy. So we can actually look at this from a very theoretical, very information theoretic perspective. So we have some papers on that. It's a very interesting problem in general. How would you have this kind of generalization properties for something like that? But I will talk about the more practical kind of view on this here. So now let's assume the encoder actually trained some neural network. Okay. So, and I want to transmit this neural network over this noisy channel, and how should the decoder, how should I deliver this over the channel that the decoder can still use it? So what are the challenges? So first of all, as in the case of image, I don't want to first train a neural network and then compress it to the capacity of this channel and then transmit it. I mean, I will show you, how that would do, but from the previous example, I saw that it's better actually to solve these problems together. So that's what I'm going to do. So now what I want to do is somehow take these neural network parameters and directly send them over the channel. Somehow modulate them directly on my waveform. So, but now there are many challenges. So how do I do compression in the analog domain? In the sense, so I have these millions of parameters. Okay, I can map each parameter to one parameter of my waveform, but that would require a huge bandwidth. I have 100 million parameters maybe. So I need a waveform that can carry so many parameters. But otherwise, if I don't turn these into bits, I don't know how to do compression in general. And then if we want this to be robust against noise, because these parameters, when they go over the channel, noise will be added. And I also want to do somehow error correction against those noise. I want to somehow, be robust, but also maybe even to be able to recover some information. So for the, very briefly, for the compression part, we can use pruning type of techniques, right? So I can try to somehow remove as many parameters as possible. That would be reducing the bandwidth. So this is basically, I can train the neural network. While training, I can take into account my bandwidth constraints over the channel. And for the noise, what I can do is that I can also try to do the, introduce noise during training, right? And this is already done in neural networks for, like robustness purposes, actually. So we introduce some randomness. But now I need to do it because that's going to happen during test time. So I need to introduce same level of noise such that the network is still robust against that kind of that level of noise. Now for the error correction, we will use some technique called this Shannon-Kotelnikov mapping. So this goes back to 50s when they were more interested in analog type of communication. They were actually not yet using digital communication. So the question is, so let's say if I have one real number, but I want to map it into a two-dimensional space because the two parameters of my waveform, and noise is added, and I want to be able to recover from this single number from these two numbers. So it's a kind of this so dimensionality expansion. So there's whole this area of space filling curves and etc. So one example would be, for example, this Archimedes spiral. So what I do basically is that I map the amplitude of my signal, the sign to this one of these curves. So if it's positive number, so I will map it into somewhere on this red curve. And where I map it will depend on the magnitude. So this distance from the origin will be the magnitude of my signal. And then I will get the X and Y coordinates, and those will give me the two parameters that I should transmit over the channel by modulating the waveform. So again, like this is, a little bit detailed, but just to give you an idea of, like how, what kind of tools are being used. But now to show you the results, again, I'm showing you the top one accuracy here for the CFAR10 classification using a small VGG16 network as a function of the bandwidth of the channel. So how many symbols I can transmit over the channel. So now you can see that this basically the orange and the green curves are, if I were to first train a neural network and somehow either try to compress or try to train a small network that could be transmitted using the channel at the capacity. Again, I'm favoring this digital approach, and still I'm doing much better with this direct approach. And here this purple one, if I use this also this expansion one. Bandwidth expansion, this somehow analog error correction, especially useful if there's fading channels. So the fading meaning that the channel quality is changing over time, and I don't know what the quality is going to be. So that requires more robustness. That is why this analog error correction scheme becomes important. And so this is, so one interesting observation here is that actually it is better to prune the network to a lower dimension and then use this analog error correction to protect some of the more important coefficients, the weights of the network compared to others. So use to channel resources to correct, to protect some of the very essential, possibly the lower layer network weights against noise. Okay, so this is now was basically yet another example of a problem, a communication problem that arises due to this, developments in machine learning. But again, we kind of solved it not using standard communication techniques, but we showed that actually we need to develop some new techniques and actually even benefit from machine learning techniques while designing our communication system. Okay, so now I will move on to a different type of problem, which is distributed training. So before I was assuming, I have some problem, I can design whatever the code, I can train it, etc. And I was showing its performance when it's somehow implemented over a noisy channel. But of course, in many cases, we will need to do some training over many nodes. So this could also be, distributed learning computing, where I mean here, when I might have actually data centralized, but I need to use a lot of this kind of worker servers for their computational power. So the computation is distributed. So I need to somehow assign them some computational tasks and be able to get the result as efficiently and as quickly as efficiently with the available distributed computational resources. I will give one example of that, but of course, another example would be the federated learning type of setting where the data is also distributed. So now I have these devices. In the federated learning case, they might be orchestrated by this parameter server, but also this can also be a fully decentralized scenario where these devices with their data and computation resources, now they need to communicate with each other to learn a single model. So in the case of distributed training, the challenges that I will emphasize are slightly different. They're not the traditional, this could even be, let's say, a big, server setting where you have computational big servers, but maybe they are distributed in the same area. Or, maybe for some tasks, you might want to use the servers, Amazon servers or whatever, but they are distributed geographically. So you need to send your data to them and then get back results. So several challenges. One of them is the struggling server. So you send the task, but maybe at that moment that server is not available or delayed, and so it will delay the whole task. So you want to be somehow robust against some of these servers not being active at that time. And this will happen randomly. So you don't know which one is going to be inactive at any point. And there's also, of course, the collusion problem. So typically, for example, you have some very valuable data, you want to train a model, you want to use Amazon Web Services, but you don't want Amazon to know anything about what you are doing. So, this, you might use different Amazon servers. Some of them might, collude. They try to, like exchange data to get your information. So you want to be private against potentially colluding servers. And of course, there's the communication bottleneck. So you also don't want to communicate too much data back and forth. So I'll give a very kind of simple example just to illustrate the type of things that we are looking at here. So the problem is distributed linear regression, right? So we have some, like labeled data. We want to minimize the mean square error. We want to train this model theta. So the yi's are the labels. So we want to minimize this squared error. And typically we use gradient descent. So at some point we have the model theta t. So if you find it, so the finding the gradient, so this is the goal. So I want to compute this to do the gradient descent operation. So now if you look at this if this data set is huge, basically these computations become challenging. And this is the case actually in reality. So in Google, they might have these, like millions, billions dimensional matrices. So this X transpose Y part, so this is just a function of your data. You need to do this once. So let's assume this is done. But this one, I have to do it every iteration. So every iteration, I have to compute X transpose X times theta t. Theta t is the current model. So this can be a demanding task. So I want to distribute that somehow. For example, I have some edge node doesn't have computational capabilities, but there are some computing servers available around. So how could I do? So now let's assume that this is some, W matrix. What I can do, I can divide it into three sub-matrices. If I have 3 computing servers, instead of multiplying this whole W with theta T, I can say, okay, why don't you multiply W1 with theta T? Every time I will send you theta T, your goal. So I deliver W1 to this server, W2 to this server, W3 to this one. And every time the new model I send, so they compute W1, Wi theta T, and then send it back to me, then I do whatever the update. But now what happens is that if the second server, for example, is struggling at that moment, then I have to wait for that to be able to do the model update. So that would give us a problem. Now, interestingly, this is a very different type of problem, but it turns out that we can treat this very similar to errors over a channel. So in a sense, now here I want to compute something, but let's say one part is in error. So how do I recover that computation? And we can do something, a completely new area of research, which started a few years ago, is that we can do coded computation. So the idea is exactly the same as coded communication. So when we communicate, coding introduces extra redundancy. So instead of sending, for example, 10 bits, I do coding, I add this kind of smartly designed extra bits, such that if any of the bits I transmitted in some random subset is lost, I can still recover the original 10 bits. So this is the idea of error correction coding. So introducing this redundancy to recover the original information. So we can do the same now for computation. So what we do is that we introduce additional redundant computations such that if any of them is lost randomly, we can still recover what we were to compute originally. So, and here, instead of dividing into 3, now we divide into 2. So basically each server now, instead of doing 1/3 of the computations, it has to do half of the computations. But now, even if, so I assign W1 here, W2 here, W1 plus W2 matrix here. This just as the summation operation, the size remains the same. So now, even if one of them is lost, I can still recover the full computation. So this is basically introducing redundancy to do against straggling servers. Of course, this is a very simple version of that, but there are many different ways of doing that. As I said, there's also the privacy issue. So I might actually not want these servers to learn anything about my data set. So for that also coding helps. So we have actually developed lots of different quite interesting coded computation techniques for this type of problems. Now, in the case of federated learning, now let me briefly also mention that. So as I said, now I don't have the data, so I cannot assign data to the servers here. The issue is that they have their data, but sometimes they participate, sometimes they don't. But the main thing is that so let's look at the very simple federated averaging algorithm. So the way it is done is that parameter server keeps track of this global model. Every time it sends the global model to the devices, they do local training, and then they update, either they send the gradients or model updates after several gradient local iterations to the parameter server, which averages those updates and then updates the global model, sends back, and they keep iterating. So this is the algorithm. Now, if we were to use, so now let's assume these are sensors, some IoT devices, they have their data and they're doing federated learning with the help of some Wi-Fi access point or some base station. So they are within the same area. So now if we were to use the standard communication protocol to do that, in standard communication protocol, what we do, we assign channel resources, this could be spectrum or time, to these devices to minimize interference among these devices. So we don't want them to interfere with each other because they're sending different data. So that would actually harm each other's transmission. So what would happen? So we would, each time, each device, participating device, they would compute their updates. Then this parameter server would divide the available bandwidth or whatever resources among them. So, and each one has to now compress its update to that level available resource and then transmit. The parameter server decodes all these updates, takes the average, and then updates the global model and sends back. Now, the interesting thing is that, so this is actually where, again, this kind of communication and computation converges. So here, what we want is actually to do the computation. So the parameter server does not care at all about individual updates. All it wants to recover is this average. And actually, wireless channel is a superposition medium. So naturally, it actually adds the signals. The signals, when we transmit them over the air, they add up. What we do in communication, engineers, what we do, we try to get our, somehow mitigate this superposition. So we want to make sure that they don't superpose. But because normally they have different information, we want the parameter server to receive base station to decode each individual message. Whereas in this case, we actually want them to add up eventually. So what we do, so we introduce this concept of over-the-air computation for federated learning. So we actually synchronize these devices, and they directly, again, as before, embed their module updates to the waveforms, and these waveforms added over the air. So we now turn air into a computation medium rather than just communication. And directly now the parameter server recovers the average and updates and then sends back. Now it turns out this gives, of course, this is much more efficient bandwidth-wise, because now everybody can use the whole bandwidth. Now we don't even care, like who is active, who is not. If they are active, they just transmit. If they are not, I don't need to care about, whether I should allocate them resources or not. Moreover, it gives natural privacy because everything is added over the air. Nobody actually hears anybody's individual signals. So it becomes a very, very efficient scheme. There's one challenge, sorry, which is very similar to what I mentioned before. Now, these models are huge. If we were to transmit all model parameters in this manner, it would take a lot of bandwidth. So the way we resolve it is similar again. So we first can prune them, but then if you prune them and try to send, the remaining coefficients, then you also need to send the extra information of where these coefficients are located, which will be a lot of information. So to mitigate that, what we do is we use some pseudo-random linear projection. This is very similar to a technique called compressive sensing. So basically, it's a way to recover sparse signals from fewer measurements. So basically, we use this as a technique for bandwidth compression in this problem. So it turns out that, not very surprisingly, now in terms of test accuracy, with the same resources, so this basically analog distributed stochastic gradient descent over the air gets much better performance. It's almost the same as error-free shared link compared to the digital approach, assuming it has, again, it could achieve capacity over the channel. So, and this is true for both IID and non-IID data distributions. So this is now again showing that for when it comes to machine learning applications, they have many very different requirements compared to what we are normally used to in traditional communication systems, which would require to basically completely think of these things from scratch and come up with novel designs specifically for these applications. Okay, so before, basically, if you want to use this in wireless channels, the scheme I showed before would require channel state information to know what the channel is, because we want them to add at the same level so that they give us the summation. So in this paper, we also show that by using more antennas at the receiver, you can actually get around this. And this was basically, I want to talk about this because it's an example again, where now you need to have also the domain knowledge to understand what these antennas do to be able to, use the machine learning solution in the right manner. Okay, so I think, so I was going to talk very quickly about how to do reinforcement learning over a communication channel, but I think it's better if I actually stop here, just to, maybe I can leave it here. So the idea is, now in the reinforcement learning is typical, we want to interact with the environment. But actually, you can take any reinforcement learning problem, any kind of Markov decision process, and take that agent. You can divide that agent into two agents. So one of them becomes the controller, which sees the state and the reward. The other becomes the agent, which actually interacts with the environment. And we can put a communication channel in between. So as if this is now a remote controlled agent. And now we get, again, a completely new class of problems, which actually turns out generalizes all existing communication problems. And also generalizes, of course, all these Markov decision processes, where now the agents and these two agents now not only need to learn how to interact with the environment, but they also need to learn how to communicate. So this is also, I would say, very interesting new research direction. Okay, so I stop here because I want to leave some time for questions. And yeah, so for more information, you can check our website. If any questions about any of these, any of our work, would be happy. Of course, I'm always happy also to recruit good PhD students. I've of course had some Turkish students, so would be very happy to have more. And yeah, and of course, if we have this book, edited volume, which talks about all these things and many different other problems, also connection of machine learning and wireless communications. So thank you very much for listening, and yeah, so happy to answer any questions. So I can't hear if, I don't know if there's...
Hocam sesim geliyor mu acaba?
Evet, şimdi duyuyorum.
Evet, hocam çok teşekkür ederiz değerli katkınız için. Şimdi soruları Türkçe alabilir miyiz?
Alabiliriz.
Tamam.
Tabii ki ben anlamazsam sorarım.
Tamam. O zaman siz bilmiyorum katılımcıları göremeyebilirsiniz. Belki ben...
Evet görüyorum ama duyamayabilirim de.
Tabii. Evet. Tamam hocam. O zaman
sorusu olanlara ben mikrofonu iletebilirim.
Evet. Sorusu olan varsa hocamızın. Haberleşme ile makine öğrenmesinin kesişiminde çok ilginç bir aslında örneklerle ele aldım Deniz hocam.
So, can you hear me? No. So, my main question was, like, you mentioned some challenges about limited bandwidth, but what about 5G? Don't you think that this 5G eliminates those challenges?
Yeah, so questions basically whether 5G eliminates all these limitations. I mean, 5G allows us to be able to use this, let's say large bandwidth, time, etc. But in the end, these are also application dependent. I mean, first of all, it's never infinite. And even 5G, like if we have more and more devices trying to learn things, exchange models, etc. So it will very quickly can become limited if we don't take this, into account. But as I said, I mean, like it's also not just about, like 5G. I mean, you can have a lot of resources, but as long as that takes time, for example, introduces latency, then that might be a constraint of your application. So that's still an issue.
The last question, you mentioned that machine learning requires more features than communication engineering. Could you just briefly repeat?
Sorry, I missed the last part. So you said
machine learning requires more features than communication engineering. What are those? Can you just briefly mention those again?
You said more features?
Yes.
I mean, more features in the, I mean, I would say not maybe necessarily like more features, but it has more specific requirements and constraints, right? So for example, like as I mentioned, if you want to do federated learning, now we need to send those models. I mean, and if you want to do it thousands of iterations, so we want to do it very quickly, very efficiently. So which might not, for example, be possible because today we have our codes and modulation schemes and things like that are designed to deliver content, and this content can be quite large, and we might not have such strict delay constraints. So now, in machine, or also, for example, if your car wants to detect the pedestrian and avoid it, and maybe some local information is required for that, so now the delivery of that information is much more critical, has to be done very quickly. Whereas, I mean, if you're just sending some data, maybe it's not as critical as that. So that's the main thing, basically. I mean, this kind of inference tasks are typically have more stringent constraints.
Thank you very much.
Yeah, thank you for the question.
Öncelikle sunumunuz için teşekkürler. Benim sormak istediğim şey aslında kusura bakmayın. Benim sormak istediğim şey aslında hem alan dışı hem alanla alakalı. Biz acaba aslında bu yöntemi özellikle afet durumlarında veya bu tip mesela 6 Şubat depremi gibi veya çok büyük bir iletişim yükünün olduğu durumlarda makine öğrenmesi acaba doğru iletişim kanallarını otomatik belirlemesi için kullanabilir miyiz? Bu konuda hiçbir çalışma yaptınız mı? Yani ben sahada çalışan bir doktordum ve bizim Şubat ayında en büyük yaşadığımız sıkıntılardan biri iletişim kanalı elinizde olsa bile o iletişim kanalının gerektirdiği gücü orada data naklini yapmaya uğraşmak ve hani o datayı çekebilmek veya o an bir bilgiye ulaşabilmek oldu. Hani en büyük sıkıntılarımızdan biri de buydu. Ve depremde de belki hani ek kayıplar vermemizin de en büyük nedenlerinden biri de buydu. Hani elimizde imkan var ama o imkan nerede olduğunu bilmiyorsun veya o imkanın nasıl bir sevk zinciri oluşturacağını çözemiyorsun. Hani mesela ben de veri bilimi ilgileniyorum doktor olarak mesela şu an ilk düşündüğüm şey bu olur hani. Yani biz bunu acaba bir acil serviste veya bir yerde bunu biz buraya uyarlayabilir miyiz?
Evet, yani çok çok güzel bir nokta. Ve yani şöyle söyleyeyim, benim araştırmam daha çok işin böyle kodlama, gerçekten fiziksel dizaynı boyutunda. Hani burada biz daha işte flexible, agile, böyle hani işte öğrensin hemen, işte hangi resource nereden, hangi bilgi nereden gönderilsin, kendi öğrenerek yapsın diye uğraşıyoruz. Ama tamamen yani katılıyorum. Aynı hani fikirler daha böyle hani diyelim ki bir sistem var elimizde, hani nasıl communicate edeceği, ama hani resource management açısından işte hangi frekansta kullanalım, mesela işte bir frekans available, işte onu hani daha verimli kullanalım. Bir başka bir hani provider'ın baz istasyonunu kullanabilelim falan tarzı şeyler için de bakılıyor zaten ve kesinlikle yani hani böyle daha yani hani her şeyin zaten normal gittiği bir durum için işte her şeyi optimize edip bir hani çözüm bulup onu uygulayabiliriz, ama hani bu tarz şeyler daha aslında ben de katılıyorum, hani böyle ortamın değiştiği, tam bilemediğimiz, ne olduğunu bilemediğimiz, bir daha baştan sıfırdan bir şey dizayn etmeye vaktimizin de olmadığı durumlar için de çok daha uygun. Yani bu tarz hani emergency communication için de var. Çok iyi bilmiyorum literatürü, ama hani böyle daha işte kendi öğrenip şeyini, hani resource'ları daha adaptif kullanma amaçlı, hatta hani 6G'nin içerisinde hani düşünülen şeylerden birisi o.
Hatta belki şey bile yapabilir hani haritalama, Shannon haritalaması mesela hekim veya sağlık verici hastayı anlatmaya başladığında oradaki hastayı anlatmaya başladığında o haritalamanın içinde biz makine öğrenmesiyle hastanın aciliyetine göre belirleyip mesela en acil hastayı anlatan kişiye ilk ulaşım imkanını sağlayabileceğimiz hani o tip bir triyajı bile biz ulaşım anında belki sağlayabiliriz.
Tabii o aslında hadi o biraz daha şeyin de üzerinde, yani daha böyle datayı manage etme, hani onu yapmamak için hiçbir sebep yok diye düşünüyorum zaten. Hani o çok sistemi şey yapmaya bile gerek yok. Hani herhangi bir communication sistemi üzerine de kurulabilir. Tabii yani hani birçok alanda işte verimliliği arttırabilecek bir şey zaten. Hani biraz önemli olan bunu çabuk ve doğru bir şekilde uygulayıp çözümleri bulup hani hayata geçirebilmek.
Çok teşekkürler.
Çok teşekkür ediyoruz. Tekrar Deniz hocamıza çok teşekkür edelim.
Ben teşekkür ediyorum ve tekrar yani özür diliyorum orada olamadığım için, ama çok iyi bir etkinlik diliyorum hepinize. Umarım bir dahaki başka bir etkinlikte görüşebiliriz.
Umarız hocam. Eğer sorularımız olursa da yine yani burada değilsiniz ama elektronik posta
Tabii
herhalde.
her zaman maille her zaman ulaşabilirsiniz. Soru için, yorum için herhangi bir
Tamam.
sebep.
Çok teşekkür ediyoruz. Sağ olun.
Teşekkür ederim. Görüşmek üzere.